So from this part, this force, we want to find part of this one which is here. That will mean we have this angle. This side is adjacent because it is close to the angle we have we know. The angle we know as this. So part of this will be here. So it means between this angle, this is adjacent and this is hypotenuse. So we have adjacent and hypotenuse, which means it will be or cos. So it means cos theta, sorry, no, cos 90 minus theta is equal to our the FA, the force here is what? Adjacent over hypotenuse, which is what? Mg. And this becomes what? Mg cos t and cos 90 minus theta is equal to FA. Now this force that is coming down here is when the ball is going, is right, the gravity will be negative to it. Okay, so we have to negate this side. Okay, in other words, we can also say that the gravity, the acceleration, will always be coming. I mean, will not be ever increasing. That means it will not be increasing forever. It will not be increasing it forever. So in that sense, we have to negate it. That is what is negated. Okay, you can also look at it as gravity when it's rising up. It's acting against gravity, so it becomes negative. So this is it. This we can rewrite as sine. Cos 90 minus theta is the same as sine theta. Because if you add cos and sine, you will get 90. So if this is 90 minus theta, it means sine is theta. When you add cos and sine, you get 90. Cos is the complement of sine, from the word complement of sine, so it complements it. So let's say if sine is, cos is 60 here, then sine is 30. You get it? That's what I mean. So if this whole thing is 60, then sine will be 30. If this whole thing is 30, then sine will be 60. So that's what I mean. So this can be rewritten as that. So we have mg in it. Okay? We have mg in it. We are looking at this. This is where we are working towards. We have mg in it. We have an equation with the length in it, and then the displacement y also in it. Now we are looking for equation which will have what? The mass and then the gravity in it. Mass and gravity. Okay, then we'll see how we can go. Okay. Now we should relate this one. We should relate this one to something that will contain omega, or that has angular velocity. The only way we can get angular velocity from force will be this force that is coming. Okay, that is bringing it back. It is the same force, more or less, that is also moving it in the circular path. Okay, right. Or let's say this force that is coming is a tangential force. Okay, that tangential force that is coming at that point. It has the point that is coming. If it is not going through a circle, if this were to be going through a circle, or it's as it is moving through a circle, there's a centripetal force that is directed towards the center, and that will be mass times acceleration in plain language, linear acceleration. But we can convert part of it, we can change it to angular acceleration in that sense, or to contain angular velocity. Alright, so we know force is equal to mass times acceleration. Now we are saying that mass times acceleration, this acceleration can be expressed in terms of what? Omega. Okay, because we have omega here, so that we can have an equation that we can represent and then put to get some expression for t. Okay, so what's the relationship between linear acceleration and omega? This is ma, is m times linear acceleration becomes what? Omega squared is minus, okay, minus omega squared. So this times here. Let me write it properly. So this is times minus omega squared. R is the radius. Now this radius that we are talking about is the radius for the simple amount of motion, the to and fro. So by the time y gets to the maximum, this maximum point, where we have these angles working, at this maximum point, y is equal to the radius for this motion, not radius for this simple harmonic motion. So that this is the same as minus m omega squared y. So in essence, we will have this sin theta is equal to minus omega squared y. Okay, we have y in there. Now let's try and then bring in, so we have y, we have omega in here. We have m and g here. Let's try and bring in the length and then the length into the equation. Which equation has length in it is here. That is why we have theta here. So we can, in place of theta, we can put this expression there. We've already said when theta is very small, it's equal to theta is equal to this if it's very small. Or sin theta already we have also found from this when it is very small that it is equal to that. So sin theta is equal to this, theta is equal to that. Because for that this happens because when this is very very small, the figures will be almost the same. So in that sense, we're going to have this. This is going to be represented by here or here the same thing. Y over L is equal to squared y. Now let's simplify this equation. This m will cancel this m. This y will cancel this. Okay, then we're going to have negative will cancel negative. Then we're going to have what? G over L is equal to omega squared. Now this is the same as saying omega squared is equal to J over L. If you find square root of this, find square root of that. So that's omega is equal to square root of J over square root of L. Now we have omega, we can put that value here. Okay, this will imply that, let me write it well. Let me go up. This will imply that if omega is equal to root of J over root of L, and T is equal to 2 pi over omega. This one, we got it from the expression that where we said omega is equal to this over T. Now for a complete rotation, the time, when you go one complete rotation, theta is 2 pi. The time taken becomes capital T. Do you get it? And this is where we add that expression for this one. So that W is equal to. So W is equal to 2 pi over T, which is the same as T. If you bring T there instead of here, T will be equal to 2 pi over omega. That's what we have. Right. So at this point, let's substitute omega into the equation. So T will be equal to 2 pi over what? J over L, which is the same as, because this is dividing into 10. So we get 2 pi times root L over root J, which is the same as 2 pi L over J. This is the equation that we have. This is the equation that we have. So this simplifies the whole thing. And I'm sure with this analogy, you can use this one for the spring as it is hanging. So here gravity will be working. When it is lying on the table, there's no gravity. Okay, then its force is equal to what? Kx minus Ks, because it will be going and coming back. It will not forever be equal. And this, you can also have the column for measuring pressure. Okay, this height, this is timing. So at this point, back and forth. So for this one, let's say height is here. So this is what is alternating. Okay, goes down, comes up, goes up, and the positive comes down, negative. So we are having that. And if you are using this, of course, then here the constant, you have constant which is J, and this is what is varying. Here we have the, what do you call it, the extension. This is going to go down by E, or to extend by E. So here we have E and J constant for this. But when it is like this, we don't have G acting because the body is horizontal. If it is horizontal, gravity is acting vertically on it. So there will be no component of gravity in the horizontal, unless it's something just less than 90 degrees within it. That is where gravity will have effect on. Right. So in this case here, there's no gravity. Gravity is out. We only have a constant K, and then we have extension E. Now all that you do is here usually takes the constant, and this will take the extension of the change. So for the spring line where there's no constant, then T will be equal to 2 pi our E over K, where T it's hanging, now gravity is working 2 pi our E over G. So it goes that way, where we have a column that is measuring pressure. Then we have our T is equal to 2 pi, G is a constant, and H is a value. So this is what you can do to get all these equations. Right? So we have 4 equations. So when you are told there is a column for measuring height, the height that it goes about, the height rises maybe 2 meters or whatever. That's too high, maybe 0.02 meters. And then we are asked to find the time it will take to go up, come down, and get back to its former initial state. Then the time is the same as the period, so you can substitute h and then g, 2 pi, you can find the time. The time is the t, the time for one complete turn to move and then come back to where you started. Okay, that's the period, right? So I think this makes the whole thing very simple. This is quite simple and straight to the point. Now sometimes you have this way, and maybe you have another way. Now, if the two waves, okay, if they come such that they overlap like this, then they are in phase. And if they were, let's say the two were sunk, or maybe other ways, they will give you one indication, something like that. Now let's say in another case, this wave A, wave B. In another case, something like that. They are out of phase. Instead of being in phase, they are out of phase. It's like this is coming this way, they will cancel. This, they are out of phase, so here to cancel. So you end up having, you don't have one line, you have maybe something like that. Okay? Then the next one you do, maybe they are in phase again, you come this way, and then maybe that way, you have it something like that. Okay, so when they are in phase, you get one production. So when they are out of phase, you have something like that. Okay. Now if you look at it from this angle, so this kind of representation, okay, this kind of representation is what we call the Lagrangian figures. So you can use this one, maybe you have two sounds, you can use it too. If you know the sound of one, if they come in phase, then you know they are the same, they have the same frequency or the same wavelength and that kind of thing. So you can use this kind of phenomenon to detect two waves or tell the characteristic of another wave when you know one. All right. So we move on. The next thing. So this can be the oscilloscope can be used like that. Now let's go to the next one. So center of gravity and then center of mass. Center of gravity and center of mass. You have this body where the mass of the mass, okay, where mass appears to act, okay, that is the center of mass. Okay, where the weight appears to be is also going to be the center of gravity. Okay, now the center of mass should be the same on different planets, okay, because that's mass. But the center of gravity or the center of the center of gravity, which is corresponding to the weight, is mg. So this is dependent on the gravity. That means the center of weight will not be, the center of mass will not be the same on different planets. That's the point I want to make. There are instances where the center of mass will not be exactly, will be lying maybe something like a curve like that. The center of mass may appear to act somewhere. Okay? Instead of acting in the body, it may appear to act somewhere. So it's not all the time that you have the center of mass or center of gravity within the body itself. Now you have stability of things. Okay, the center of mass will tell. So let's say if this is it. This is the center of mass. If we turn it, we shift this one a little here. This center of mass, if it's here, maybe this will stand. If it turns and then maybe it comes over here, this will fall that way. If you turn and comes over here, it will fall that way. Right? Now the other point, let's say we have that on the floor. If we lift this one up a little and it's still within, it will fall back. It will not turn to another one. If we lift it this way, it will fall back, then to another one. Okay? But there are instances maybe you have a cone, a ball like that. This will be, it will keep on rolling, but the center of gravity will be the same. So that's more or less like the neutral phase. And this one, you just shift and then come back to the former range. Okay? So for something to fall, usually the center of mass is more or less where everything is acting. So if it's out of stability with respect to the support, then it will fall over. Okay, so you can have a neutral position like this, you can have the unstable, and you can have the stable kind of position. Okay, right. So this can be something that you can look at. So we move on. Now let's look at pressure. According to, if this is the body, okay, if you put, let's say, cup in here and it's floating, so the law of flotation, okay, flotation. Let's look at it. Now, so let's say this one is floating like that. It's floating. Floating. If it's floating, if this is floating like this, what's going to happen is one. This has the mass mg pushing it down, and then the fluid is also acting with the force against it. We call that the upward force or the thrust, upthrust. Okay, the upthrust. Okay, right. Now the body will float when it is floating. So far as this body, if it is floating, okay, if it is floating, then the volume of this volume of fluid that has been displaced by this body, that volume of fluid, okay, will be equal to the weight of the mass. So this is according to the law of flotation. Okay. Now, according to Archimedes' principle, this body which is in the water is more or less pushing down with its force, and then the water is also coming up with the same force. Okay. Now, the amount of upthrust, the amount of force the fluid is also exerting against this body will be dependent on how much force this one is also going down with. Okay, so that if upthrust will be equal to the weight of this one, as it's will be equal to the amount of force this is also pushing down. Okay, force by body. Okay, so this will be the Archimedes principle. So you see that if the body is floating, then it is its weight which is pushing down, and then the upthrust, if the body is floating, then upthrust is equal to the weight of the body. If it is not floating, okay, if it is not floating, then it's the force with which it is moving down. The force with which it is moving down, that will be equal to the upthrust. Okay. In other words, you can also also say that just like the flotation we said, the volume of water displaced, okay, the weight of that volume is equal to the weight of the mass. Floating body, the volume of fluid, the weight of the volume displaced is equal to the weight of the mass. Okay, good. So in the same way, the upthrust, the force on this one, if this one is floating, once it's floating, it has some force downwards. That force downwards is equal to the force upwards. Okay, But because it is floating, then the force upwards is equal to the weight of this mass. To get the weight, we also know that the mass of and the weight of the fluid displaced is equal to the weight of this body. Or let me put it this way. First, we have this. This is the floating body. There's an apparatus on it. This is also going down with empty. And then there's the volume. So we have first the volume of fluid, okay? Then we have updraft, so that we get the principal. And then this is the weight. Now we are saying that this weight is equal to updraft. In all instances, the weight that is going down, the force with which this one is going down, or the force with which this one is being pushed down, is equal to the updraft. Okay? And then we are saying that the weight, if there's fluid displaced, the fluid displaced is equal to the weight of the fluid displaced is equal to the updraft. Okay? So the weight of the fluid displaced is equal to updraft. Now we know that when the body is floating, it would have displaced some volume of water. So the volume of water it has displaced, the weight should be equal to this one, because if it is floating, it's the force on it is just its mass times gravity. So if it is floating, so its volume of fluid is equal to updraft. Volume of fluid displaced, okay, is equal to updraft. But when the body is floating, then it is also equal to the weight of the object. So we have three things here. Put in mind, okay, V is equal to U is equal to weight, something like that. Put it this way. So this is for floating. So this has in it Archimedes principle and then the law of what? Flotation. So Archimedes principle is the first one. The volume of fluid, the weight of the volume of fluid displaced is equal to updraft. And then the law of flotation will say that if the body is floating, then the updraft on it is equal to the weight of the body, which is the same as the weight of the fluid. Okay, so once you know this principle, so you can just give V, U, that is what, or you could say U, V, W, which is the alphabet, U, V, W, okay? That can be to remember. So updraft is equal to the volume of water displaced, and it's also equal to the weight of the body if it is floating, okay? So updraft, this will be newtons, this is volume of water displaced, so the weight of the volume of water displaced. You can calculate it, okay? You should remember that 1 liter of water has a mass of 1 kilogram. Okay? 1 liter of water has a mass of 1 kilogram. Okay? So this one can help you or guide it. 1 liter is the same as 1,000 mils. That's 1 kilogram. So this can guide you. So UVW can stand for the Archimedes principle, can also stand for the law of flotation. Okay, right. So we move on. So still on pressure. Now, if this is fluid, let's see here. Now, no matter how you turn this one, if this is the fluid and then you put something in it, and this is straight, this is not there. The water level will be the same, the level is the same. This is because the pressure, the height is proportional to the pressure of the fluid. Okay? The height is proportional to the pressure of the fluid. So that is what I want you to note. Now, so if you want to find the pressure in anything, you know pressure is equal to force over area. Force is what? Mass times gravity over area, which is that. Okay? But area can be given as what? The length times breadth. Right, so that's it there. And this is what I mean. Let's say we have this volume of fluid. This is in a cylinder. Okay. Now pressure is equal to force over area. Right. Now the force is equal to mass times gravity over area. How do you get the area here? How do you get the area here? You know the area of a cylinder. This is also area. The volume of a cylinder is cross-sectional area. This is the length. This is the cross-sectional area times length. Okay. So in this case, we can see that area is equal to volume over length. Okay. Area is equal to volume over length. Now let's put this one here. We're going to have mg over area, which is now what? Volume over length. Okay. This is going to be written as, this is going to turn outside. So we're going to have mgl over v. But we know m over v. This m over v is the same as density. Let's let this one be density. So you have this L. Now L here that we have is the height, is the column of, so is the height, it's also the same as height. So rho is equal to G H, and this is pressure of fluid. So the pressure of the fluid is equal to the density of the fluid times the acceleration due to gravity times height. So that because this is going to be constant for that fluid, this is going to be constant, this is only the only variable. So that pressure is directly proportional to the height. So the height will tell height here, the height or the depth. The depth will tell the pressure at that column. So if I want the pressure here, pressure here, pressure here, pressure here. So see here, the column is this. So the pressure here will be greater. Now, if you come here, if you want the pressure at this level, you see the volume of fluid on it is less. So this pressure will be less than this. If you come to at this level, then this is what you're going to have. So this pressure here, so it's not the depth, the pressure increases with the depth. Right. Of course, the atmosphere is also exerting pressure on this. That's what I want you to remember. This is the atmospheric pressure by air is acting on it. Okay, so this column is what we're going to have. Alright, so that is this one, that's what I wanted us to. And pressure is equal to rho times gravity times time. That's pressure in fluids. Okay, that's it. Go to the next one. Now, Torricelli, he is linked to pressure. So 1 torr is the same as what? Your 133.3 Pascal. Okay, so that will be let me write it well. Same as 133.3 Pascal. That's the unit for pressure, which is also the same as 1 millimeters of mercury. Okay, so this you can keep in your mind. So 1 torr is the same as 133.3 Pascal or 1 millimeters of mercury. This is usually used in most textbooks. Okay, that's what you find. Pascal is a standard. Okay, but you can also compare it to that. Millimeters of mercury. So this is telling you millimeters. It's the height of the column of mercury that is supported. That's going to give you that. Right. So it means 1 torr is the pressure that can make mercury rise by 1 millimeter. Right. That's it. Let's move on. So you see that the pressure is the same at the same height, or the same age. Pressure is the same irrespective of how big the fluid is. Okay. Now let's look at how the submarine operates. So the submarine can submerge and then can also come up. Now how does it use the principle of density, pressure, and so on? So what it does is it has some columns that are filled with air. Okay, so if it wants to sink, then it will allow water to flow in. If water enters, the water will increase the weight of this one. You know, density is equal to your mass over volume. So the same volume, so if water is allowed to enter the submarine, then its weight is going to increase, or its mass is going to increase. So once its mass increases, then the density will increase. So the density, it will be denser than water, and then it will sink below the sea level. Now if you want it to float, then the water will be let out. When it's let out, mass has been reduced, so density reduces, and then it floats and comes up. That is the principle that the submarine uses to come up and then go below, submerge. Right. We move on. Right, let's look at this kind of motion, which we didn't talk about when we were talking about motion. Now, if we have the body like that, and it's moving, let's say it is rotating. As it is rotating, it is also moving. Okay, so here we have two kinds of movement. We have rotational, which you can use your omega, your r, okay, angular velocity, radius, and then acceleration you can use to describe. Then this is, as it's going straight, this is translational. So this is straight line motion. It has both rotational and translational energy. So if you want to find the total energy or work, total energy or work being done, your kinetic energy in rotation plus kinetic energy in translation. Now as this is going, there is friction between it and the tire, okay, and the surface. That friction also takes some an energy, so energy loss, okay, or energy against friction must also be accounted for. Okay, so this is how it's going to be. Your translational straight line, your translational energy will just be, of course, the kinetic energy formula, mv squared. Okay, and this is what is going. Okay, but this one will have to be written in terms of rotational. Okay, you must find an expression for v in terms of this or that. And that can, v squared over r is equal to acceleration, or v is equal to r omega. Okay, so if you put this one here, then you're going to have what? You're going to have what? So this, how it's going to have half m r squared omega squared, something like that. 4. So you add them, so you just have to get the principle. The principle I want us to get is it is rotating, at the same time giving a translation, is going against friction, so these are the energy kinds. Now if the reason why this will not be the same as this, it could rotate without moving. So if it is rotating and moving, then the two are different. It could rotate without moving. So if it is rotating and moving, the two are different. The same thing, the flywheel principle. So the principle of the flywheel also the same. This one here is turning like that. Okay, this will be rotational, kinetic energy, rotational. Okay, this is also descending. So this is some sort of kinetic energy also going down. because at every point this will have kinetic energy and it will have a potential energy. Okay, this mass will have kinetic energy as it's moving. It also have potential energy until it reaches the floor where everything becomes like kinetic energy gets to zero. This also gets to zero, right? So this is one way. But just take the component. The rotational is on its side. The linear motion is on its side. If there's height in it, kinetic energy also comes in, and that is the point. Okay. Now, if what happens is if something is rising, something is rising. Let's say it's going up. Okay, that's kinetic energy. At every point, the kinetic energy is converted to potential energy until maybe it gets here. When it gets here and it's no longer moving, the kinetic energy has been completely converted to potential energy. This is half mv squared, and this is what your mass times gravity times height. Okay, these are principles you should get. Okay, so that when you're working things out, you know. Right. Okay, so we move on. So we come to another principle we are looking at. We call the Bernoulli's principle. Bernoulli's principle. No, Bernoulli, they are a big family. They were into finance, mathematics, and so on. So the Bernoulli's principle states that if you have this column of fluid, okay, if you take this unit, okay, the pressure here plus the kinetic energy, potential energy plus the kinetic energy, then it's always a constant. Okay, that is if you express these ones in terms of pressure. So this in terms of pressure and this in terms of pressure. Okay, then if you add them, the value will be constant. What does that mean? So this means that we are looking at pressure per unit volume. So if you take this as the unit, okay, the pressure here, the pressure there, plus the kinetic energy per unit volume, plus the potential energy per unit volume, okay, right? The pressure force, the pressure there per unit volume, okay. This per unit volume must be constant, okay. Now the pressure is this, kinetic energy is of half mv squared over volume plus what? mgh over volume. Now you realize that this will give you density, this will give you density. So P plus half density V squared plus density, which is rho gh, is equal to constant. Now what does this principle mean? This principle that we have here mean? Now the principle is that for this unit, this column, if pressure increases, one of these must reduce so that we still have a constant. Okay? So if two of them are increasing, then definitely this one must reduce.